Coefficient theory in KK theory.
Okay, so I guess I'll begin. So I already told you the story about the tree, so I guess yeah, I automatically put this up as soon as I saw January 14th here. So anyways, so let me tell you how I structured the talk first. I usually don't like to do this to tell you in advance what I'm going to do, but here I kind of thought it was more necessary so that when we go along the way, you have some support kind of with you. So the way I view this topic that I'm going to discuss, it's basically basically these two things up above, but I also included this one here. So there's an abstract machinery that is at work here. And so I'm going to try to describe the abstract machinery completely independent of what I'm going to say in between. And then, of course, there's an application of this machinery that happens. And then I will also try to, in between, like describing machinery and then applying this machinery, also give some down-to-earth examples, the way I view things. So it's like more relatable so for people who maybe not aware with it, haven't worked with the machinery, or probably they're not aware of the application because it's the new work. But I will talk about this in a minute. So as you can probably tell, so the bulk of the work that I'm going to describe today, which is joint. Well, I'll say it in a minute, but the bulk of the work goes in this part here. By the way, can you see my arrow that I'm waving around? Okay, yeah. So the bulk of the work, of course, goes on here in the application only because some very smart people already described and created this machinery that then applies here. But as it happens usually with the category theory, some people like to call it also abstract nonsense. I mean, the machinery that works here also needs some real down-to-earth computations when you want to really apply them. So anyway, as I said, the bulk of the work, okay. So bulk of the work goes on here in the application side. And what I'm going to talk about this today, especially in this corner, is joint work with, yeah, that's how I go, with Ralph Meyer, who is here. I saw he asked about the tree, so he can maybe also chime in if there's some questions and stuff. So it's our joint work from basically already last year. Well, it's January, so it's last year. And the name is the Universal Coefficient Theorem for Actions of Finite With C-star Algebras. And there's a preprint archive you can check out, or it should be published very soon. But the right topmost corner that I described is basically all contained in this article and with much more details than I will be able to describe today. So, okay, so we have our background, the machinery application. I will actually try to indicate here and there which one am I describing, where am I describing machinery, am I describing application, or am I describing examples or whatever. Okay, so let's get down to business. But before I do, I actually took the liberty of doing this because the recordings were available publicly. So I just want to remind, so we had this first week of so some kind of background lectures, right? And the second week of research talks. This was how it was intended in the beginning. So we had some very nice lectures. So the machinery that I'm going to use mostly is a machinery of a triangulated category and doing specific things in a triangulated category. So I want to just remind you of how we got to triangulated categories during our first week of lectures. And so maybe I wanted to give you a specific screenshot of the board. So sometimes people forget and do not remember the exact definitions, especially if it was new for you. However, you might remember the exact moment that something happened. I find this is happened. So we had this very nice lecture. I think it was second lecture, maybe. Yeah, the second, because the stable things were discussed in the second lecture from Bastian Knossen, and it was introduction to stable categories. And here you can see that we had this proposition that the following things are the stable category, what things are equivalent, and so here it was mentioned, it was not proved strictly because we never strictly defined triangulated category as we'd never strictly defined it, but it was mentioned that we had this co-fiber sequences here. You can see X, Y, Z, and these things turn into exact triangles like X, Y, Z, and then we had this sigma X here. You can see, and we saw that this proposition was discussed that homotopy category of stable infinity category is a triangulated category, right? So this is where the first triangulated things were introduced, and we had we saw the triangulated categories are like consist of this kind of diagrams, X, Y, Z, and then we had this suspension functor, which was an equivalence on triangulated category side, and then it had an adjoint on infinity side, but whatever. So X, Y, Z, and so this kind of things. And then we also, I think it was the next day or the same day, so we had another very nice lecture from Ulrich Bunke, so the KK theory from point of view of homotopy theory, so other introduction, and we saw this category. Okay, so there's some notations that were different in different talks. So here, this category, we had this category, infinity category called KK, and then we had the homotopy category of that stable infinity category, but that was denoted by KK naught. But I tried to do that. I tried to follow that also and try to denote the KK. So as you understand, I'm going to be using this KK naught side, the classical bivariant K-theory category, which from this point of view of the talk was a homotopy category of a stable infinity category of KK. Here you can see that we did some localization. This was called KK, and then we had KK naught, which somewhere here we had so here is a theorem that KK naught with omega and exact triangles, which were explained how these exact triangles are created. I think right here, yes. Yeah, completely positive contractive sections. So all this was explained. I just want to remind you the snapshot. And it was explained that this is a triangulated category. So we had a concrete example of a triangulated category, namely KK naught. But whatever was called KK naught in this talk, I'm going to call it KK, because if you drag around this zero long enough, you see that it really clutters things, especially when you have to add the degrees here and stuff. So I just call it KK. And whatever in Ulrich's talk was called omega, in the next days it was called sigma, and I will stick with sigma, which is the more traditional thing to do in the classical KK theory. So I will use, but I'm not going to dive into that. So we call it sigma for a suspension, and this category KK that was explained to us. Then again, we had a very nice talk by Christian Voigt that now we know about the triangulated category KK. We know what the triangulated category is. So we got to this talk, and then we had a locally compact group G. And then we also found out that there's a category KKG. Basically, this is what we denote by KKG. And I will just mention, if you take G to be trivial group, then you recover the category from the previous slides. So this, whatever was called KK naught, but I will just call it KK. So we found out that there is this compact group, and then we also knew that there is a Kasparov product, but you can make it also G equivariant. And this thing, KKG, also turns into a triangulated category. Does it say here? Maybe on the next slide it does say, yes. On the next slide it says that this thing was a triangulated category. And we have a suspension. Now this time it's denoted as I will do it. So the suspension factor is just tensoring with C0. And then we saw that there are diagrams of this form where, by the way, there's this. So in the Bastian's notation, we had ABC sigma, and now sigma is on the other side, and the cone construction. So it's the opposite convention, but you know where this comes from, because algebras are opposite of topological spaces. And so if you have a triangulated category in general, the opposite of the triangulated category is canonically triangulated. So this doesn't really bother anyone. So you can view your triangles either this way or the other way. So let's just ignore it for a moment. This is too much detail that we do not need right now. But we saw that this guy is also triangulated. These were triangles, this was suspension. Okay, so what next? So what am I going to focus on? So we know what KKG is, we know what KK is, we know what triangulated categories are. I'm just going to assume it without defining any further. But I wanted to point out here why I like this slide specifically, that it says Christian said this think here that the category KKG is triangulated, and then there's a dash, that this allows one to do homological algebra. And this is what I'm going to hinge my talk on today, that the machinery that I'm going to describe, by the way, you can see that this has this prefix application, meaning that the machinery was of triangulated category. Now I'm applying this machinery to KKG somehow and describing it as a triangular category. But put that aside. Coming back here, so it says that the fact that KKG is triangulated, it says that I can do homological algebra there. And that's what I'm going to do next. I'm going to start try to explain the machinery of homological algebra for a general triangulated category. What does it mean to have homological algebra with triangular category? And then try to apply it in some contexts for KKG, for specific KKG. But first things first, what is homological algebra? Off the top of my head, I came up with this definition, which maybe many people would agree it's so general. So I define homological algebra as like systematic organization of computation methods to study structures, very general, but I added through notion of exactness. So you have this, you must have this notion of exactness, and then using that, you study different things. So you probably know, using chain complexes, yada, yada, short exact sequences, and so on. And now what I have here, I want to force this philosophy on this category here. This is T, by the way, fracture T or Gothic T. So there's a triangulated category T here, and I just remind you what it means. It has these triangles A, B, C, sigma A. So it has diagrams of this form singled out that satisfy some axioms. But okay, so you have diagrams of this form, and many people, I think it was done also here, when they talk about this, when they do not want to define the axioms that this diagram satisfy, they will just say, oh, they mimic the axioms, or they try to emulate the axioms of short exact sequences in abelian category. So somehow this is already a candidate. You should think of it this way, of a short exact sequence. And what my aim is now that I have these candidates for short exact sequences in my triangular category, and I want to define exactness somehow to do homological algebra. So I want to do homological algebra in T, and eventually, of course, this is as I defined it, this is a computation methods, right? So I want to maybe compute the hom groups in my category, which is the most important thing you probably want to compute in one category that we're looking at here, right? So this is what my aim is. And I will also, I wanted to describe the procedure of how I would like to do this. First, to construct a homological algebra, I will define what exactness is. Once I have a notion of exactness, then this will grant me the notion of a projective object, meaning if you know what exact is, you can say which functors are exact, and maybe you will say that representable functors from this represented by some object are exact, then this object can be called projective. So if you have a notion of exactness, you have notion of a projective object, which of course gives you a notion of a projective resolution, which then grants you a notion in favorable case of a derived functors, and so on and so forth. You build the homological algebra. So this would be my procedure. So, but again, it starts with exactness. The first thing you might think, because I'm still in the machinery realm here. The first thing you might think of is, okay, so I kind of nudged you in a sense that, okay, I know what exactness means in a triangular category. Exact are the exact sequences which come from triangles, by the way. I was hoping I had, okay, anyways, I don't have it, so my hope is gone. So, but there's an observation, if you have worked with homological algebra before, there is an observation that if your category is non-abelian, somehow you always need additional data to get started. If you just declare all exact triangles in your triangular category T to be exact in some sense, and then follow my procedure, then if your triangles, these exact triangles, these diagrams are short exact sequences, then there's a fact you can prove the fact that if you have a representable functor represented by some object A, let's say, and you apply it to a triangle, it gives you a long exact sequence, no matter what the representing object is. So those are called homological functors on a triangle category. Most of you have heard about it already, probably. And so if you have something like this, then if you declare all your short exact sequences to be exact somehow, then all your objects will be projective in this sense. And so the homological algebra you will recover or you will get will be completely trivial. Everything will be projective, everything will be exact, because all the structure you have in a triangulate category are exact triangles, and then you're declaring everything to be exact. So you kind of lack non-exact things to measure distortion. But that's, again, philosophy aside. What I'm going to do instead, I'm going to instead pick a homological functor. By homological, I mean functor that maps exact triangles to long exact sequences. But if you are not familiar with this definition, you can just think of it as a functor at the moment. So I pick this functor into some abelian category, let's say A, and I mentioned in the parentheses here that everything is stable, meaning that T has this suspension functor, and I also assume that this abelian category on the right side also has some kind of suspension shift functor, and all of my functors and everything will commute with that suspension. I'm going to say it once and forget it because it's a technical issue. Just know that everything is stable and everything commutes with suspensions on both sides. Here it's usually a degree shift. Here it's the suspension functor that you already have here. So I pick this functor from T to A, just some functor, and I do not declare all triangles to be exact. Rather, I call this triangle to be exact if when I apply H, I get a short exact sequence. So some of my triangles now will become exact somehow. And those of you who are familiar with this, of course, this is completely determined by the fact that this map here from C to sigma A has to go to 0, you can see. So this triangle continues on that side also, and this other map has to go to 0 as well. So it's completely determined which maps go to 0, by which maps goes to 0, and actually, so by the kernel of H, and actually the kernel of H is the one that determines the homological algebra, not the H itself. But let's skip this for a moment and just think that we have a functor and we declared which triangles are exact. And then I just continue doing the usual stuff. I will call a chain complex over T, so some long chain, H exact, so it's exact relative to H, if when I apply H, I get a long exact thing. Okay, and then I have a definition. I'm just following, if you remember my procedure that I had on the previous slide, I'm following that procedure that I call a different functor from T to some other category B here, H exact, if it maps H exact triangles, the ones I singled out, to short exact sequences. So basically what it means, if I go back here again, so H exact triangles were completely determined by this maps that are by the kernel of H, basically, like what things does H map to 0, namely this maps here. And what this means that F will be H exact if it has a bigger kernel, somehow bigger or the same kernel. So the motto you can think of this is what is invisible to H somehow is also invisible to F. So it has a bigger kernel, and then I will call F H exact. So I have now definition of relative exactness somehow on my T after picking H. And of course, now I again follow my procedure, and I will call an object in P H projective if, by the way, this is a hom functor. Somehow, I think the notation everybody else used was hom T, but I will just use a T and parentheses. This just means hom, right? People use this as well. So the hom functor from P, from T to abelian groups, if this is H exact, then this guy will be called H projective. Okay, just the usual definition from classical definition, mimicking the classical definition. And this, of course, then provides what I can talk about H projective resolutions. So these are things that are like this. And then I can talk about the derived functors. How? If provided, which I will always assume that T has enough projective objects, meaning I can construct one-step projective resolution for an object. Then I again. That means I can, for every object here, I can construct a projective resolution. It goes here. This is a homotopy up. So homotopy of T. So this is just a notation that this is where the chain complexes end up. So this provides a functor here. Then I pointwise, so I have projective, so from A, I create a projective resolution of A, then I apply F pointwise, so I have some functor F here, so I apply F pointwise, and then I take the homology, and this will be the derived functor, exactly mimicking the classical definition of the left-derived functor here, and so everything works. This is basically what I'm saying. So the classical things carry over. You can also do this for right-derived functors and covariant functors and so on, but this is details. So you have derived functors. So, okay, so I built some, and then it continues to build the homology theory. But okay, so now what? So I built all this machinery relative to some functor H in my triangulated category. And now let me just say a couple more things, maybe go here and say a couple more things. I said that the homology on my triangle, this relative homology theory that I just constructed depends on H, of course, right? And I said that it really only depends on the kernel of H, kernel meaning on morphisms, which morphisms does H map to 0. This is what it depends on. And so if two functors share the same kernel, they will induce the same homology. That's what I'm trying to do. So there might be many different functors that induce the same homology theory, same projective object, same derived functors, everything on T. But it turns out there's a universal amongst these guys. So if you fixed your H, that means you fixed the kernel of your functor, then there's a universal functor, I will call this U, among all the functors that induce the same H homology here. I call this guy. And so T, universal meaning in a classical sense, right? So if you have any other H-exact homological functor G, I call it G here to B, then it will factor uniquely through an exact functor G bar, meaning so there exists a category AU, which is a nice abelian category, and a universal functor U, such that everything else which is H-exact will factor through here. Okay, so what? So this is also a general construction that was okay, this is a very general construction. This is like you go to some finitely presented functors here. So this is a very nice abelian category that you end up here. And what is happening is that why I mentioned this is that now this is an abelian category on the right. This has honest to God homology on it, meaning homology that comes from real projective objects and kernels and images and everything else. That exactness comes from kernel equals image and stuff like this, and short exact sequences. And it turns out that if you have a universal functor, then homology theory, the real one on AU, and H homology theory on T are identified somehow. They are very closely related through U. And what I mean by this is, for example, if you take real projective objects on the right side, and you take relative H projective objects on the left side, this is projective TH and projective AU, they are equivalent as subcategories here. So for example, and the more importantly to us, I showed you how to define derived functors of, so if you take any F from T to B, any homological functor, homological again meaning mixed exact triangles to exact sequences. So if you take any functor here, there will be F bar such that F bar living here on this side, such that if you first go with U and then derived functor of bar, so it will be a derived functor F. So this relative derived functors are computed with real derived functors through U somehow. And specifically, this X here this is basically a definition here. So for F, if I will take a representable functor, so if I take F to be a home functor, then the derived functors of home functor, of course, are called X. So then X, this relative X functor, which is just by definition the derived functor of a representable functor, will be computed by a real abelian X functor applied first when you have to apply this U here. So you compute this universal invariant, and if you want to compute now the relative derived functors, all you have to do is you push your computations to abelian side if you have computed u and au, and then compute the easier x here. Easier. Yeah, it's easy to say, but okay, anyway. So again, so relative functors are computed this way. So it's very good if you have something like this. So, and now, okay, so you might say, all right, but how do I find this AU and U somehow? This is mysterious to find the universal guy. And there's a specific construction that always constructs you the universal approximation. So by the way, I will call this, I will use this, I called universal abelian approximation here, but I will always use this language that this is an abelian, universal abelian approximation of T with respect to H somehow. I will use this lingo. So when I say I'm a specific universal approximation, I will talk about the one of the approximations that you can actually calculate and build sometimes. So from now on, I really want to specialize to KK. So I'm assuming things that are true in KK. So I'm assuming that my triangulate category has countable coproducts, right? So from now on, I assume this always. And now I have my T and I want to build this universal approximation. How do I do this? One of the ways is I fix at most countable set C of compact objects in T. Compact means that home functor commutes with countable coproducts from home functor from this object's commutes, but we're not going to use that any more than here. So you fix some countable set of nice objects in T. I call this set C. And now I actually view this Gothic C is the same as C. I view these objects as like almost like a full subcategory sitting inside T. I will explain this more because this is crucial. But I said almost because if I have two objects, C and C prime, the objects that I chose, the hom in my Gothic C from C to C prime will be almost, well, it's like the hom in my triangulate category from C to C prime, but I put star here to indicate that I have graded it on integers, meaning I consider all possible suspensions of C here from n being -1, 2, 3, 4. So for example, if my T will be later will be KK, this will be only 1 and 2 or 0 or 1. Whatever, so 1 and 2 because of the bot periodicity. But generally, you will have a Z-graded thing here. So this C is basically like a small subcategory that you fixed inside at most countable object T, and you considered homs, but not only homs, but also all possible shifts of the hom functor somehow. Okay, you did this. And then, of course, you have this natural Yoneda functor. How? So from your triangulate category, maybe this side, every object you can map to the category of additive functors, meaning for exactly as it's written here, every object is mapped to a Yoneda functor this object maps to hom functor from object C to A, where C runs over all C, and this is a graded thing. So for every object you look at the hom functor from this object into A, and this is the Yoneda embedding you do so for every object now you get a functor that makes every object of C into abelian category, which is graded because of the star here. So this is the usual Yoneda construction, and it turns out this is the universal exact homological functor. Okay, what does this mean? Okay. So you have a universal homological. So this, by the way, I also consider only countable things here. So only things that take values into countable things, but this is also just a technical assumption that we need for KK. You're probably already aware, so many people have mentioned things like this, separability, countability, and so on. And so we have this embedding. So every object is mapped to just collection of homs, basically, and natural transformations between them. So, and okay, why is this good? Now, okay, I have this universal invariant, so universal homological approximation of some U, and then there is this very general universal coefficient theorem, somehow in very general setting, stating this. So I fixed this my Gothic C, the small subcategory inside T. For all intents and purposes, you can think of it actually as a subcategory sitting inside T. So I fixed this C, and then I generated a triangulated subcategory from C. So I look at a local, so basically localizing subcategory, triangulated subcategory. You can think of it this way also. Close down the coproducts. The smallest one that contains C, this is the category, this is the notation here, the smallest local subcategory that contains C. And I look at the object sitting inside there. This is what it's usually referred to in KK as a bootstrap class, something generated like this. And then I look at any object in T. Then as soon as I do this, then since I already have this universal approximation, I have this right half plane conditionally convergent spectral sequence like this that converges this xc, meaning this this abelian x that converges to this home functor in T, which I really wanted to compute, but this is again very hard to calculate. The very good thing happens that if your objects on the abelian side, so if you started with your object A in this bootstrap class generated by C, but if your objects have projective resolution of length 1, the real projective resolution on the abelian side, this UC is already an invariant applied to A, you're in an abelian world. If this has a projective resolution length 1, this here degenerates and you get a short exact sequence like this, that the home functor from A to B, this in this triangulated category, is approximated somehow very nicely by real abelian home functors in this universal world. So this is a very general universal coefficient theorem that you can see. And this is the machinery that I wanted to explain. So now I'm going to go into an application. So once you have this machinery, what is the strategy? What is the game that we play? Well, I play over and over, that what you do is you start with some class of objects, basically. Usually you have this already in mind, that these are the objects that I want to classify. Usually it's called a bootstrap class. You already start with something that your C generates somehow. You start with some class of objects B, I call it B. I want to study this, and then I want to pick nice enough, as small as possible maybe, C, such that C actually generates my B. And then I will, for this C, I will construct the universal approximation UC, and then I will have the universal coefficient theorem if I'm lucky enough that I chose C such that this UCAs have projective resolution of length 1. This is the usual game, and since I think the authors are also here, I can't go on without mentioning the classical universal coefficient theorem, but I want to put it in this context as I described. Let's say our triangulated category is just KK. KK not in Ulrich's first talk. So the classical KK, so separable C-star algebras. And what I do, I pick, so first I have to, as I said, I have to pick my Gothic C. So I just pick one object, complex numbers. So I pick one object, complex numbers, then the universal invariant in generality that I described, T goes to functors, A goes to things, turns into what? T is now KK, functors from C opposite to abelian. This opposite is because, of course, you put it in the first variable here, but I will explain in a minute that in more detail. So from C opposite is just one element you chose, so one object, namely C. So you get functors from just one object C to abelian Z graded. Now, functor from one object to abelian group Z graded, basically, so remember, I'm looking at all, so here it is. So I'm looking at all representable functors from C and sigma C, because both periodicity I do not have to consider all the Z. So from one object to this is just picking two subgroups here, basically. So it's like from point to C, you just you know the drill. So you really get abelian categories of Z2 graded because, and then your map becomes, your C-star algebra is mapped to KK complex numbers to A because you picked complex numbers, and KK from sigma C to A, which is basically, this is a K theory, K0 and K1 by Green-Yule. So your functor is just a K theory functor. And our machinery tells us that this is the universal invariant, and hence, because every Z2 graded here abelian group will have projective resolution of length 1, this is well known, you will have a universal coefficient theorem by Rosenberg and Shohei, which are authors are here, and you have a very celebrated theorem that if A is a separable C-star algebra, then if A belongs to subcategory generated by C, because I just picked C, one object, so this is called the classical bootstrap class, there's a short exact sequence of Z2 graded abelian groups like this. Of course, it will probably the theorem was not stated this way because it was stated differently. As I said, the game was to have a bootstrap class to begin with and maybe then find and classify things in there. But in this machinery, this is how it fits. Okay, so now we go to the application and we dive into our whatever our paper describes that I put up in my second slide or whatever. So now I'm looking at KKG. We saw this in Christian's on Christian's slide. So you have actions of G on separable sister algebras, but now I will consider just finite G, right? This is what our article concerns. So I have KKG and I have fixed the group G finite. So again, as I said, the game is that you have some class of sister algebras that you want to do something about. And the class that is relevant here, the equivariant bootstrap class, so-called BG, I will denote, is actions on type 1 sister algebra. So G actions on type 1 sister algebra. This is what I want to classify basically. And it is a well-known fact, you might also be aware, that this actions on type 1 sister algebras, this BG inside K, is generated by induced sister algebras from matrix algebras. This was also I think it was also Christian Stokes when he gave a definition of this, what induced sister algebra is. It's not too much of importance to us, so I'm just going to leave it as it is. So what you have is that you have a matrix algebra which has H action for a subgroup of G. So you consider all such matrix algebras with H actions, and then you induce it back to G. These are called elementary sister algebras, and these are the ones who generate bootstrap class, right? And so this is proven by Meyer and with Emerson, I think, and Ambrogio in that paper that I might be mistaken. So actions on type 1 sister algebras are actually exactly this, generated by this thing. And also, I just want to give you a side note if you could not recall the definition of induction. If for matrix algebra, you just put complex numbers and you look at, you have, of course, the trivial H action on C and you induce it back to G. It's just the continuous functions on G mod H, basically. So continuous functions on G mod H, of course, are in BG. This is a ridiculous statement that I have here, but what I'm trying to say is that continuous functions on G mod H are amongst the generators of my bootstrap class, right? So these are here. And here comes our first theorem from the article, which is actually due to the remarkable result by Arano and Kubota from 2018, we just gave it yet another push to put it in this context, is that you do not need all this induced and sister algebras here and all the subgroups. It turns out that objects of this form for cyclic subgroups HG already generate the equivariant bootstrap class BG and KKG. So now it very much simplifies our problem, if you recall, because what probably you already guessed it, what I'm going to is I want to classify these objects using the machinery of picking the generators of my bootstrap. This will be my Gothic C, but now I do not have to pick all of these generators, all the possible matrix actions on matrices and then inducing. Rather, I can only take much simpler generators, which are continuous functions on G mod H, and then even not all subgroups, but the cyclic subgroups are sufficient, which are very nice in some sense. And so now I do this, I do what I said. So now I will construct the universal invariant for exactly for this class. So KKG for finite G again. So for C, what I can pick is I can take continuous functions G mod H when H is a cyclic subgroup of G. So I pick this sister algebras inside KKG with this obvious G action. And then the universal invariant written very abstractly here now becomes from KKG instead of T. So I call this functor CK star G for cyclic subgroups and K theory, basically. So what you're mapping to is functor from cyclic up, for cyclic up is just this guy's here, CG mod H is for H cyclic, to Z2 graded things. And what does this CK do? There's just not enough place to write here. It maps group, so it maps C star algebra A to KKG, the star again for grading, from CG mod H to A. For all cyclic subgroups, you have to consider them all together and all the maps between them, because this is like a functor, right? And this is basically, again, I will not do this here, but this is an induced algebra. This is basically K theory, H equivariant K theory of A for all cyclic subgroups. So this is rather remarkable that the universal invariant from the actual, if you have actions of a finite group G, only involves cyclic subgroups of G somehow in KK+H of A, and you do not really need to do any matrix actions and so on. And there's by the way, there's so let me just go back here. There's a famous Georgian saying that if you sinned, you better tell. Somehow it comes out this way, meaning that we did, well, at least we did spend quite some time trying to do before discovering this result, that actually try to classify all these things here, and this is more complicated and involves more complicated things than what I'm presenting. So to actually take into account all the possible generators and not know that you only need cyclic subgroups here. So this road was also taken, but this happens. But in this case, when you only consider cyclic subgroups, there's also a very nice result by Ivo dell'Ambrogio from 2014, when he classified that if you have this functor that A goes to H equivariant K theory for all subgroups, he was doing some other thing. Well, he was also, yeah. So anyway, so if you consider this functor, this is what they call a Mackey functor in the category of Mackey modular representation green ring. If you don't know what this is, the only takeaway here is that he actually computed this functor, and now taking into account our result that type 1 C-star algebras are generated by these things, and you only need to consider even less. You only need to consider the cyclic subgroups. You can, to compute this thing and compute what this abelian category actually is, what you need to only do is you just restrict Ivo's results to cyclic subgroups. And basically he has everything computed, and then you have your functor thing computed as well. But I gave you application, I gave you machinery, and I also should give you an example now to kind of bring everything down to earth. So the very simplest example I will consider, which is not completely like a cyclic subgroup, but the first non-cyclic subgroup one encounters, it's the Klein 4 group. So it's basically Z mod 2 times Z mod 2. So it has 4 elements, right? 0, 0, 0, 1, 1, 0, 1, 1. So, and it has 4 cyclic subgroups, basically. So it has 5 subgroups in total, right? And 4 cyclic subgroups. Then named the trivial guy that is generated by 0, 0. Then Z mod 2 guy generated by 1, 0, 1, 1, and 0, 1. And then the 5th group is the V itself. This is called V, by the way, for Phia, like line 4 group. And so V itself, but this is not cyclic, so we do not have to include it. So for objects that generate my subcategory of V actions on type 1 C-star algebras, only thing I have to consider is V mod trivial, should be V mod the trivial group, so continuous functions on V mod this guy, 1, 0, generated by 1, 0, generated by 1, 1, and generated by 0, 1. You do not have to consider V mod V, which is the complex numbers, and there's an extra generator here. This int VV means nothing. So there's an action on 2 by 2 matrices. So there's an action of V, non-trivial action of V on 2 by 2 matrices that comes from a projective representation of Klein 4 group. So you have this. So if you didn't know the result, you'd have to also probably consider, and this is the road taken, as I said, consider this generator, which further complicates things. But it turns out these generators are redundant, and these things already generate the thing. And here is the diagram of that is after Evo's results, this thing is calculated. So what is this diagram? Imagine this whiteboard is KKG, and inside I picked these 5 elements. Continuous functions on V. So I'm considering V actions on sister algebra. So inside I picked continuous function on V, continuous function on V mod 1, 0, V mod 1, 1, and V mod 0, 1. And now this should be considered as a subcategory sitting inside my thing. So I also need to consider all the morphisms. And it turns out there are 2 morphisms here, 2 morphisms here, 2 here, 2 here. And then there's induction and restriction things, if you're aware with Mackey functors, like representations, induction, restrictions, induce. And so this is how my category looks like. This is my categories of cyclic subgroups sitting inside looks like. And my universal invariant in this case looks like that every sister algebra A is now mapped to, you had 5 representatives. For each one, you had KKV from this guy, from this guy, from this guy, from this guy. So different K theories, basically. And then there's also maps between them induced from the maps between the objects CV mod 10, CV mod 11, and CV mod 01. So this is what this thing looks like. And by the way, I wanted to show you that basically this is a module category. So on the left side, you see my generators again, the cyclic thing on the left side. And on the right side is what an object A is mapped to. And I want to show you how this thing, you can view it as a ring, right? So you can view this, if you've seen something like a path algebra, but like a category ring. So it's generated by this, the ring generated by the arrows, and the multiplication is the composition. And if you cannot, so for example, if you want to multiply this arrow with this one, you get 0 because it's not composable. So you can assign a ring to this category. Many people talked about ring set categories being basically the same thing. This is what is happening here. And of course, this ring acts on this module. So this becomes a module acted by this ring. Of course, how? Like if I have this arrow here from V10 to CV, of course, it induces an arrow from here to here. And that's why the C op action was written down there. So this basically, this cyclic things is basically a ring that acts on these modules. And if you have a map from here to here, of course, it induces a map from here to here. So you have basically modules over this ring here. So if you actually compute this category completely, you compute the ring over which the modules you are looking at in your universal invariant. And in our paper, of course, then you for free, once you compute all this, by the way, CK star was this assignment is CK star, just to remind you. And now again, we just go for finite G. We forgot V, which was just a given example. And now you for free get a theorem from machinery that if A is an action on type 1 sister algebra and B is in KKG, yeah, because see, A is a action on type 1 system because we know that it's generated by cyclic subgroups. So A is an action of type 1 system and B is anything. Then you have this spectral sequence that you can describe here. So this spectral sequence is approximated by this X function, which can be computed. You know the ring, you know the modules here. Okay, but of course the question is, can we get a short exact sequence? That is a universal coefficient theorem. Do I have length 1 projective resolutions? On the nose with this invariant, this is not true. This is hopeless. Things are too complicated for that. But what I'm going to do instead is I'm moving towards the universal coefficient theorem. There are 2 ways you can go. Either you enlarge your invariance, you enlarge your fracture, so your Gothic C, to include more things, and maybe so you have more K theories you're computing or more invariants you're computing of your sister algebra. This is one way to go about it, and maybe hope that if I compute more things, I more closely approximate things and maybe get length 1 resolutions or whatever. This is one way. Another way is, if you're a student of group representation, is that the modular representation theory of groups, you know, that becomes, well, relatively easy at least, or of which the group order is invertible. So we're going to use this philosophy, adopt some ideas of Manuel Koller, which there's many computations that go in here. And what I'm going to do, again, I have finite group G. And remember, this category is the one that I just described. These are modules over this cyclic ring that I showed you the diagram of. So it's the same category. What I'm just going to do is I'm just going to invert the order of G there. So if G has, let's say, in Line 4 group, it has 4 elements, then I invert 4, which is the same as inverting 2. And if you look at this here, then you can prove that it has projective resolution of length 1, this thing. So all the objects here will have, once you invert this, will have projective resolution of length 1. So this is very close to UCT now. So we can actually explicitly compute this localization, what this is. This is actually, as I say, it follows the ideas of Manuel Koller here. But now the question arises, if I find the class in KKG, so I changed the target category, right? I had the universal target category and I changed it. Maybe it does not approximate anything. You might think this way. But now I will find a class in KKG that this, by the way, I made a shorthand, this thing, it was too cluttery, and I just called A. So AG minus 1 is the universal thing when you localize G. So what class does this AG minus 1 approximate universally? If I find this class in KKG that this guy approximates, then I will have the UCT for that class. And that's where the avenue takes us. And now I'm identifying this class. And this class is identified by the divisible sister algebras. And what are this? So I fix set of primes, so S are some set of primes, 2, 3, 7, whatever. And a separable G sister algebra is S divisible if multiplication by the prime, meaning P times the identity here, is an isomorphism in this endomorphism ring. So it's invertible for all P in S. So I will then call it, say that it's S divisible. And then by MS infinity, I denote the UHF algebra of this type. It's not too much importance for this talk. This is just some object in my KKG. Now, if you read Blakadar's book, this is how localization there is defined of, but anyways, so this is some object here. And there's a proposition that S divisible objects, that means the objects for which this multiplication by P is an isomorphism. First of all, they form a subcategory, I will call it KKS inside all my algebras. And so remember, I showed that type 1 sister algebras are generated by this CG mod H's. But now if I multiply for cyclic H, if I multiply each H by this object here, so there is this object MS infinity, this UHF algebra, which when I multiply, this guy consists precisely of those S divisible objects that are inside BG. So they are actions on type 1 system. So it's the intersection of BG and S divisible objects are exactly generated by these things here. You can see that I again identified this Gothic C now that I can use and show that in case of this Gothic C, exactly so. So by the way, from now on, I will, this S was just a general set of primes, but now I say that this S is a set of primes that divide the order of G. So it's like divisors of order of G. So if order of G is 6, it's 2 and 3, basically, right? So because when you're inverting the order of G, you're inverting basically all these primes that are divisors of G, right? So now this is S is fixed. And now I define this S divisible algebras, and you you already know I know suspense is not killing you. I spoiled it, but the functor that goes from S divisible objects to this AG minus 1 is the universal abelian approximation. And now I get the UCT for free because I know that their projective resolution of length 1 here. So if A and B are in the S divisibles and A belongs to the equivariant bootstrap class in KKG, right? Then the universal coefficient theorem holds. And of course, then there's this, by the way, this one I was not, this was true always for universal coefficient theorems, but I want to mention it here since I still have like 5 minutes, that the functor, if you have this functor and you have the universal coefficient theorem for now for S divisible things here, this functor induces a big bijection between isomorphous classes of now S divisible objects in G equivariant bootstrap class, meaning actions on type 1 sister algebras, and isomorphous classes of objects in this abelian category, A G minus 1. Okay. Then we have this button here that no time is left, but since we have 5 minutes, we can not press that button. Very good. And talk about a very nice application that this thing has, namely to Kirchberg algebra with finite group action. So if you're not really the guy of classification of sister algebras and you come from homotopy, well, you can kick back and relax for 5 minutes. But what is a Kirchberg algebra? Kirchberg algebra, we mean a non-zero, simple, purely nuclear sister algebra. And there's also a remarkable result by Gabe and Sabot that any G action on a separable nuclear sister algebra is KKG equivalent to the pointwise outer action on a stable Kirchberg algebra. And two pointwise outer G action on a stable Kirchberg algebra are KKG equivalent if and only if they are co-cycle conjugate. Okay, and now we can apply our theorem and say that if further this thing is S divisible, meaning there's this functor, remember the F functor from the previous one, there's a bijection between the set of isomorphous classes of objects in this abelian category and the set of co-cycle conjugacy classes of pointwise outer GXs on Kirchberg algebras because of here, that belong to the G equivariant bootstrap class, meaning actions on type 1 system, and are S divisible. So for S divisible things here, you can, and we also have a criterion when the guy is S divisible, by the way. But anyways, this is beside the point. So this is a nice corollary that you can put one more pebble on this classification program, I guess. And finally, I will just, since I also have to complete my circle that I draw in the beginning of machinery application, and then in the end, go to the example. What will happen in our example for, let's say, so if we have the Klein 4 group, which is Z mod 2 times Z mod 2, of course, there are 4 elements. So 4 elements, so you have to invert the group order. When you invert the group order, you're basically inverting 2, right? So what you will find here that this category A that I had, AV minus 1, you will find, I said we have explicit calculation, you will see that it's just integers adjoin 1 over 2 10 times. Basically, that's what you will get. Why 10 times, you might ask? Where did the 10 come from? Where it comes from is there 4 copies of this Z1 to come from the trivial subgroup. Remember, we had 4 cyclic subgroups, trivial one, and then 3 subgroups of Z mod 2, so order 2. So 4 copies come from a trivial subgroup and the representations there, whatever. And then 3 double copies will come from 3 non-trivial cyclic subgroups. So what we find that this AV minus 1 is just modules over this ring here. So countable modules over this 10 copies of Z1 half. So it's so if you, let's say, if you have some actions, type 1 actions on C star of this sort with V actions or so, you know that if your thing is 2 divisible, your C star algebra, then it's completely classified by isomorphous classes of modules over 10 copies of Z1 half. Yeah, and here is actually, this is written out. I didn't remember that. The isomorphous class of 2 divisible objects in V equivalent bootstrap class in KKV are in bijections with 10 tuples or 2 divisible Z mod 2 graded abelian groups. So this is a nice little application for V, but of course you can do it for any group if you invert the group order. This is all I wanted to say. Thank you very much.
Let's thank George for the nice talk. So, are there any questions?
Covered too much ground, I guess.
Yeah, So maybe let me start with the question. So without inverting the order of G, do you have any results on the homological complexity of this category?
Without inverting, where was this? So this is what you get for free, basically, if you're not inverting anything. You get a spectral sequence of this. Again, this is just the same functor here, but you get a spectral sequence that conditionally convergent thing. And I think you also get some other, this general machinery also has some corollaries you can use here. But the next step, which is work in progress along this lines, is to actually add more objects to this guy here. So for invariant, you can also consider, for example, not only this one, but in triangle, the cones that these guys create. And our hope is that if you consider a bigger invariant, you actually can get a UCT for finite groups. And if you're aware of the result by Manuel Kolle, when he considers just Z mod P for prime P, those groups, for that, if you actually, then you have just two groups here and the cone, he does actually get a very remarkable result to get a UCT, but, oh, it tells me my internet is unstable. You can still hear me, right? So basically you can get the hope is that you can get a UCT if you enlarge this, but if you don't, the free thing that you get is this, basically. The convergent spectral sequence and not the short exact sequence.
Thank you. Maybe next. I think
So-
Uli first raised his hand. Sorry, Uli.
I just wanted to ask, so your S divisibility condition, is that the same as the fact that it tensorially absorbs this UHF algebra?
Yes, that's basically that is in the article, yeah. So it's a KK equivalent. So A would be divisible, you mean in this sense, if it will be KK equivalent to tensored with MS infinity, yes.
Okay.
A tensored with MS infinity will be KK equivalent to A if A was S divisible, yes.
Okay, thanks.
It's proven in the article, you can check it out.
Mhm.
Go ahead, Uli.
Yes, so essentially what you describe is somehow the way to calculate this co-limit over the orbit category of cyclic subgroups. On the level, to calculate the homotopy groups of the co-limit of the K groups over the cyclic subgroups. And so, you can also think of, the first thing that would come to my mind is filter this category somehow and get the spectral sequence from this. So is this somehow related? Is your section, or is it something completely different what you do?
To get, can you repeat to get what? So my internet.
I would try to somehow take the main filter the cyclic subgroups by, so somehow they are mapped. One cyclic subgroup can map to another one. So somehow there's a filtration of the cyclic subgroups, of the category of cyclic subgroups. Yeah, and I would try to use this filtration. Yeah, then to get a spectral sequence. Yeah, and so
yeah, maybe so.
Is your spectral sequence the same or is it different?
This thing here, let's look at this example. This takes into account all those inclusions of subgroups here. Those inclusions of subgroups inside each other actually induce these maps. This maps here are actually induced by inclusion of the trivial subgroup into these three things. That's where these things come from. So somehow this filtration, that information is not lost. It's encoded here. So these two arrows, basically, one of them, this one, I think, encodes that the trivial subgroup sits inside here. The other one is it's like a Mackey functor, induction restriction, probably where that thing. And this arrows basically This one's encode the representations of this subgroup. So basically, all information is kind of sucked out from this subgroup structure. But the remarkable fact is that only the subgroup structure of a cyclic subgroup somehow suffice. Yeah. This is by Arano and Kubota, yeah. And of course, conjugations are also induced things here. So So all the structure is already sucked out G.
So let's turn off the recording.